Welcome, paleopedologists. We're now working our way through the different soil-forming factors. Remember, clort. Now I want to do this one here, which is topographic relief. That is basically the landscape position of a soil. What can we learn about landscape position from a paleosol after we've considered the different kinds of soil features that form in different landscapes in the modern world? Well, what we need, of course, is a topo sequence. And it would be really ideal to use that topo sequence as a basis for topo functions. In other words, we need to find a place where topography is varying, but the other soil-forming factors are invariant. That's going to be a relatively small area because climate and vegetation vary over quite a bit of distance. Now, the topo function is not to be confused with catena. Catena is a lateral distribution of soils. Because a catena is just a general lateral distribution of soils that can be observed in the modern world. Catena is not necessarily a topo sequence. And the classic case is the case of Geoffrey Milne in what used to be called Tanganyika territory, is now called Tanzania. The classic example of a catena or lateral relationship in these Tanzanian landscapes was to have an environment of a wooded grassland. This is where the big game is, like you would see in the Serengeti Plains or Ngorongoro Crater. And then there are copies of just bare rock, but also large areas of a rock which is called laterite, which has a kind of a forest called Miombo. The Miombo forest is a dry woodland of East Africa. This is the wooded grassland, which is called Naika. So already we're in trouble here because we have different sorts of vegetation. That's breaking our rule of keeping things constant. The lateritic crust of Miocene age is above a mottled zone. This whole thing is about 4 meters thick or so. Then there's granite, which is basically early Cambrian. Whereas the Nika, the wooded grassland, the classic African wildlife habitat, is on Pleistocene volcanic ash, because the Rift Valley area of Kenya is quite volcanically active. This is a smectite or Pleistocene volcanic ash. This is a Miocene age laterite from the Middle Miocene, when forests were much more extensive than they are now. This is a catena, and we still use the word catena, meaning the lateral distribution of soils on the landscape, but it is not a topo sequence. For a topo sequence, we need to have something that is rather more subtle. One of the classic examples is Jewel Bog. in Iowa. Jewel Bog is in an area which is entirely grassland. There's actually a relief now from the bog down the bottom here of 1 meter or so. The whole thing is in grassland. There is on the hilltop, the grassland has a Mollichepipedon, but there's a bit of a BT horizon. This is an alpha sol. This is a mollisol. This is a histosol down here, P, forming in the bottom of this swale. The whole thing is on loess and till. The till is from the last glacial maximum, around about 20,000 years ago. The loess is Purulus, around about 13,000 years old. So the whole thing is the same age, so that's good. The timing's good. The parent material is pretty monotonous, loess and till, well-mixed glacial debris. The organisms are primarily grassland, and the climate, it's a very small area, just about 100 meters or so. It's from this that we can get a topo function. Not that these topo functions are all that useful. We can look at the changing degree of acidity, the changing degree of clay formation, the changing degree of weathering up and down this profile. It's not anything that is particularly useful for studying paleosols, unfortunately, but it is an example of a topo sequence, and these are topo functions. I've never been able to use any of them, but they are there. The distinction then between a catena and a topo sequence. There are, however, a lot of pretty nice indications of topographic relief that we can actually look at for paleosols. And although these aren't quantitative topo functions, they're nevertheless of interest. One of the most interesting ones, indications of topography that I've found in my career, is soil creep. Now, you've probably seen this if you've been in the country, looking at road cuts where there's steeply dipping schists, and then as you go up into the soil profile, those schists sort of bend over into the soil layer, like so. And you can sort of see that fence posts that were originally put in erect are now dipping down, and trees have a kind of a stem bow to them. Stem bow. Stem bow is kind of an uncertain indication of soil creep. Fence posts also kind of bad too, because, well, they can just fall over, can't they? But sometimes in these situations there are quartz veins in the schist. And these quartz veins also bend into the soil. They parallel to the schistosity or to the strain in the original rock, and then they bend over as they go toward the surface. I saw one of these some time ago. It was really quite remarkable in a paleosol that was 1 billion years old at a place called Shiegra, which is in the far wilds of northwest Scotland, where there are pegmatite dikes coming out of a gneiss, and these pegmatite dikes consistently dip in one direction. The gneiss is down here with corestone weathering. It's quite a thick profile, about 3 meters. And then there's the gneiss down in here. The pegmatite dikes keep going. Pegmatite is a quartz-rich later intrusion or crack fill in a granitic rock. This is indicating that this particular paleosol developed on a slope, not necessarily a very steep slope. 10 degrees is actually enough to get substantial soil creep, but on a slope nevertheless, and this direction was downhill. The whole thing is dipping now. It's very old, about 1 billion years. It's overlain by fluvial conglomerates of the billion-year-old Applecross Formation of the Torridonian group. These sorts of features are very, very interesting because for Precambrian paleosols, in this particular case, we were trying to use it to look at atmospheric composition. This indicates that the soil was actually exposed to the air as opposed to being glayed, being waterlogged and having a low oxygen content, which was its own thing. If you find these examples, and sadly they're quite rare, they're quite useful indications that your paleosol, now in a sedimentary sequence, was originally on a hillside. Cumulic or cumulative horizon. These are also rare in my experience. And a part of it's kind of a semantic problem. In a sequence of sedimentary rocks, it's quite common to find bedding. And then you start to move up into what looks like a pretty well-developed soil. This is a BT horizon. And then maybe an E horizon. With root traces in it. That would be an A horizon. And then another root, another root, another root, another root, and then bedding. Bits of bedding and different roots. What's happening here is that the soil is formed on this sediment, which has bedding. It formed quite a well-developed profile, all right? And then the floods started to come in, interrupting the plant growth. Maybe the trees persisted for a little while, but eventually they gave up. I prefer to call this, you could call this a cumulic horizon, a cumulic A horizon. That's one possible interpretation. I prefer to call this an AC horizon. So this would be a let's say a salmon, a sandy entasol, and this would be a xerolf, a dry climate, summer dry climate alphasol. I prefer to separate them out. So it's a matter of opinion. Generally, what we're looking for in recognizing a paleosol is a sharp top, but in some cases there isn't a sharp top. In some cases there is an interval of weakly developed soil formation in which the rate of the colonization by plants is keeping pace with the sedimentation. So on the one hand, you could regard this as just a part of a cumulative A, an expanded A, as the plants coped with increased flooding and eventually gave up. Or on the other hand, that would be a cumulative or cumulative. All right. On the other hand, you could just call the addition on top a salmon. Either way, it works. But the implication, of course, is that this soil formed in a relatively low-lying condition. Xerolf, for example, is going to have a water table down here. When these are forming, the water table was evidently periodically quite high to introduce floods. The floods were introducing sediment into this material. And water table is by far and away one of the most effective predictors of the landscape position of a paleosol. Now, the water table is kind of an unfortunate name, actually. because the here's the landscape like so. It actually is not tabular. The water table outcrops in wells, and it also outcrops in streams, but it tends to follow the topography to some extent. In relatively low-lying areas. Of course, if this is a big hill, there's not going to be a water table there. You'll have to go down a long way before you hit a well of usable water. And then the other aspect of table, which is kind of a misnomer, is that it varies quite a bit. So in a flood, the water table's up here, it's flooding the floodplain. In a drought, the water table is down there, and it can vary really considerably with time, with inputs of moisture. There's strong water table fluctuation. Now, in this kind of a situation, you can have three alternatives, pretty much. You can have below water table, within the zone of fluctuation, and above water table. Now, in a sense, most of our paleosols in the rock record are going to be within the zone, but generally speaking, we do actually find some moderately well-drained paleosols, even though eventually they were overwhelmed and buried. What you're going to get in a situation like this is a kind of a profile which is fairly normal looking. So it's going to be a profile that has a full suite of horizons, an A, maybe an E horizon. That's alluvial. This is organic plus mineral. This is the leached. Leaching requires the water table to be quite a bit lower. A BT, that is clay enriched. And a BT will form by the washing of clay down toward the water table. Peter Berman pointed out very effectively, with some experiments even, that you cannot transport clay down into a soil material unless it is above the water table. The filling of the cracks with water impedes the downward transport of clay. It impedes that particular structure. There's a BK horizon. This is an horizon of carbonate nodules with carbonate. That BK horizon actually forms in an environment where the carbonate, the mainly low magnesium calcite, is precipitating in a dry environment. It's actually coming out of solution by dehydration. So the water table has to be at least down to there to form these various features. These are the features of a well-drained soil. Now, that's not to say that there's the occasional flood that will enable people to cruise around on boats on the top, but mostly the water table is down here to enable the formation of these structures. If you're below the water table, on the other hand, in a peaty soil, you're mainly below the water table, although it may fluctuate a little bit down into the profile. You can get an O horizon, that is peat. The A horizon will have tabular root traces in it. That's A, mineral plus organic. There may be nodules of pyrite. This is the BG horizon. It'll be pyrite if it's intertidal. It'll be siderite if it's fresh water. The whole thing will be kind of green and gray, and then there'll be more bedding from the parent material down here. This is red with hematite. This is gray, and maybe even a little bit golden with pyrite and siderite. What's happening here is the water table is up here, and it is keeping the whole soil relatively starved for oxygen. These are the sorts of soils that you get in coal measure sequences, just one coal seam after another from the metamorphic alteration of coal. These are the sorts of paleosols you get in calcareous red beds, the red bed sequences. Within the zone of fluctuation, we get a profile that has intermediate characters. It can have a thin O horizon, usually not too thick, because to form a thick peat, you need to have a very delicate balance of subsidence and accumulation, because there's a very delicate balance of the roots being able to breathe. Roots have to breathe, they respire, so they can't be buried too fast, and we'll go into the rates when we get to time for formation of soils, and the decay of the material that they deposit on the soil during the year. So in an environment where it's not subsiding at a rate that can bury the material faster than it can be decayed, then you get a very thin horizon. If it's subsiding at a rate which is fast enough for the material that is shed by the plants to actually carry from year to year to year, then you start to develop a kind of a peat. There can be, so this is peaty, but not very peaty. There'll be some root traces down in here. There may be an E horizon, which is leached. There may be a BT, which is clay, which is mottled, speckled, like the leopard's coat, with these dark reddish spots in amongst a background of rather grey material. These are the features of soils in which the water table fluctuates between here and here. It is reducing to create the grey patches, and it is oxidizing to create the mottles from year to year. The zone of fluctuation is coming up and down. There can also be a BK horizon, which is carbonate. And that, of course, is above the bedding of the C horizon. We're talking about soils in sedimentary settings now, like floodplains. So this is the bedding of the flood material down in here, which is the parent material on which they're forming, in a pretty classic place to find lots of these things. We also find in the BT and in the BK horizon, we find iron manganese stain. So iron oxidizing bacteria are working there, but not fully oxidized. And we find hematite in the models as well. Sometimes we find hematite mixed with siderite or with pyrite in these soils that are within the zone of water fluctuation. Now, we've talked about burial glaciation, for example. Burial glaciation actually mimics these conditions pretty well. It's a phenomenon of burial, not a phenomenon of the original soil. And so that's the trick, isn't it? To try to distinguish between the original glaciation and the burial glaciation. These mottles in a soil that forms within the zone of water table fluctuation are what we call very strong mottles. They're very, very rich red colors, and sometimes they are concretionary. So we have carbonate and we have these concretions. Because within the zone of water table fluctuation, we're going to actually get banding of the precipitates of hematite, siderite, even calcite, alternating one to another. One of them reflecting the dry season precipitate, and the other one reflecting the wet season precipitate. Now, ways to get at these different kinds of paleosols in the fossil record are by looking at roots. In the waterlogged soil, the roots form a tabular pattern. They are not deeply penetrating. In the well-drained soils, the roots are deeply penetrating. They reach down into the soil as if there's no stopping them. And then so if they hit the water table, they spread out. Roots respire. Roots are actually using the sugar delivered by the leaves from photosynthesis in order to grow and to take nutrients out of the soils. We can also get clues from burrows. Most burrowing organisms in soils are air breathers. So if we're looking at a rabbit burrow, for example, water table has to be above that. If we're looking at an earthworm burrow with the fecal pellets in it, that means that we have to be above the water table. If we're looking at cicada burrows down in the soil, simple escape burrows, yep, they would drown if there were a water table above that level from the fossil burrow in the soil. Bee burrows, most of these creatures that I talked about last time, these are air-breathing creatures, and they cannot tolerate being below the water table. There are exceptions, however. One of the really interesting exceptions are crayfish burrows. In soils of the Mississippi River, it's quite common for crawdads or crayfish to burrow well down into the water table, sometimes even 2 or 3 meters. So the crawdad here with his nippers and his body and his segmented tail is living actually in a little pool of water at the bottom of the burrow. It's actually capable of living in a waterlogged condition. Now, crayfish often line their burrows with pellets and with other cementing materials, which makes them somewhat distinctive. Also, they tend to reach really very deeply in soil, but then the same is true of termite and ant nests. They can also reach quite deeply into a soil. With a bit of experience, you can pick a crayfish burrow apart from an ant nest or a bee nest or some of these others, and you can get a pretty good idea of what the soil was like from the burrows of the organisms that were in it. We can also look at structure, soil structure. When we see a set of platypeds, that is an indication of a waterlogged soil. The peds are not much differentiated from the parent material itself. When we see blocky, angular, and granular, and columnar peds, those are indications of good drainage. Columnipeds even are indications of a dry climate as well. When you have salt-affected clays, these salt-affected clays are actually bulging up at the top to form a kind of a dome on top of the column itself. Blocky, angular peds, these are formed by the shrinkage of the soil. In this intermediate ground, it's quite common to see that the blocky peds are somewhat slicken-sided from shrink swell behavior. But of course, that's going to happen with compaction as well. When an ordinary well-drained soil, which has got blocky peds, is buried by a compaction, all those peds will scrape against one another to produce slicken sides that are pretty characteristic. And then finally, there's micromorphology. These sorts of soils are acepic, meaning no sepic plasmic fabric, undulic or inundulic. Undulic, of course, is more or less isotropic, and inundulic is almost completely isotropic with kind of cloudy kind of fabric to it. This is what we get sepic fabric, where you get the sorts of fabrics that indicate shrink swell behavior in the soil profile as the soil was forming, like marsepic, mosepic, insepic, skelsepic, these different sorts of fabrics. These sorts of soils, which are permanently waterlogged, have a microscopic structure which is similar to that of ordinary sedimentary rocks. These have the very, very characteristic sedimentary structures, the very, very characteristic micromorphology or birefringence fabric of modern soils, which is preserved in paleosols actually very well indeed. So there's a lot to this, and usually it's not too difficult to figure out where you are with respect to the water table when you're dealing with a paleosol. But there are lookalikes. For example, burial glaciation can mimic some of these effects, and compaction can mimic some of these effects. A lot of soil scientists who look at soils for the first time get confused by both of these things and will jump to it being a seasonally glade, a seasonally waterlogged soil originally, when in fact it was probably more likely one of these. The consistency in individual successions is also kind of a clue. We do sometimes get coal measures in red beds and vice versa. We do get intergrades between all of these on extensive sedimentary floodplains. However, generally speaking, in a sequence of red beds, you're going to get largely these. In a sequence of coal measures, you're going to get largely these. And if one of these turns up, it's kind of a surprise, and you might want to suspect that something profound has happened, like a major sea level change or some tectonic disruption. So that's how you tell ancient relief in an individual paleosol. Now, potentially, of course, with paleosols, there's the potential to figure out the entire landscape. Wouldn't that be great? And this is the kind of work that has been largely done with paleotopography in paleosols. We could do it, we would think, on the basis of lateral variability. That would be great, if possible. Many years ago in Pakistan, in 1980, when I was on an expedition, we were actually mapping a whole set of parallel sections to try and make a panel diagram of the distribution of paleosols and sediments. So this is the blue-gray sandstone. These are Miocene age. And they are important because they had a a fossil called Ramapithecus, which at that time was thought to be ancestral to humans. That later on it turned out to actually be ancestral to orangutans instead. And we had the buff sandstones. The blue-gray sandstones were the channel deposits of the ancient Indus. So the Indus would expand its channel bed and be very, very extensive. And these buff sandstones were foothill streams, not the axial drainage of the Indus, which cruised from the Himalayas all the way down to the coast near Karachi, but the streams that were draining the foothills of the Himalayas are now buff because they were rather more weathered. These are the sort of tributary drainage to the Indus. And then between these, there were all these wonderful paleosols. And we've measured section here, section here, section here. It seems simple enough to correlate the paleosol from one section to another and make a panel diagram which would show where the paleosols were forming with respect to the channels themselves. Just one soil on top of another. These particular soils were a whole variety of alphasols and iridosols and septosols. Some of them were glade. So this was very, very promising indeed. Except we also had on the same trip a paleomagnetician by the name of Lisa Taux, who was putting in a magnetic stratigraphy for these beds for each individual section. And this is a technique where we look at the orientation of magnetic minerals, magnetite, but also hematite, and a few others do this to look at normals and reversals in the section. And she did these sections. And the surprising thing was that the change from magnetic orientation went like so. It cut across these paleosols. Now this is an isochron. We know this is normal. This is reversed. We know that this happens within a few thousand years, this normal to reverse transition. It's a technique of dating rocks because the normal and the reverses are often different lengths. We can often figure out which ones they are from a well-dated sequence of volcanic rocks and get a very accurate age for any part of the section. This isochron made nonsense of this correlation. It turns out we can't just correlate them laterally. And the reason should be apparent to you. When you think about the terraces on the Willamette Valley, these are landscapes that are alluvial and they are terraced. And so the ancient landscape is cutting in a confusing fashion. Just correlating one paleosol in one section to the one in the next is actually very difficult to do. Now, maybe in certain cases, if you had one really thick soil, which indicated a particularly prolonged period of formation, you could get it. Maybe if you have unusually thick soil. The other place where you can do this is if you have a volcanic ash. It's very difficult and expensive to do all this paleomagnetic work, particularly on many duplicate sections like this. But volcanic ash is something that is very distinctive sometimes. Some of them are rich in lapilli, some of them are rich in sanidine, some of them are granules, some of them are fine-grained. Individual ashes can also be radiometrically dated and be distinct in different sections. It will bury the whole landscape, like the city of Pompeii. and the volcanic ashes come out from a Plinian eruptive column after over a period of a week or so, and then they blanket the landscape. That actually fossilizes the landscape below. There's a very famous case of this called the KBS Tuff, after Anna K. Berensmeyer, who was mapping in the Kubifora region of Kenya. And this tuff actually preserved a landscape of rutisols and vertisols underneath it. And you could reconstruct a whole landscape that way. But just straight up correlating is difficult, because alluvial systems have nested terraces, which we can also see in the fossil record, including in the Painted Hills of Oregon. Now, vertical variability. A more common way of getting an ancient landscape is by using Walther's facies law. The basic idea is we measure a section. I always like to put grain size on my sections so you can see them more clearly. So this is clay, silt, sand, gravel. I like to reserve this one here for coal or clay, where there's no plastic component to it. We can have a sequence of soils that are developing between sandstones, where we have a very clay soil, like so, a thinner one, and here's the bottom of this paleochannel, which is like this, a very sandy and gravelly rock. Here we have our paleosol here, paleosol here, paleosol here, paleosol here, and another paleosol down in here. We can map this like this, and you'll see quite a few of my papers have it this way, where we have a weakly developed soil here, where this is moderate development. This would be strong. This would be weak development, a thin profile. A moderate developed would be a soil developed about equivalent to what you get in a in post-glacial times. Over the last since the ice has retreated from North America, pretty much that's the size of this one. Here, these are soils that form over periods of only 1,000 or 100 years or so. This, of course, is a point bar cycle. A kind of a sequence that you get about 10 meters thick or so from the deposit of a meandering stream. In a meandering stream, you have a big river bend, basically. Here's the point bar. Here's the cut bank of that stream. And that stream is creating a levee that goes out into well-developed paleosols. Okay, it's starting to look a little bit like this again. Here's the conglomerate, here's the sandstone, going out through to here. Here's the cut bank. This is the point bar. Here's the levee. Where you park your Chevy, the levee is created because that's where the trees grow. And when the flood comes down, the trees baffle the floodwaters and it drops coarse material there, so it's a slightly raised area. Here's the floodplain here. This is where, in the flood pictures, you see people boating on fairly still water. Here are trees out here as well. This sequence reflects this geography. With a vertical sequence like this, you can envisage this kind of a lateral variability. This whole idea of reconstructing a lateral distribution of environments from a vertical distribution of sediments is called Walther's facies law. Johannes Walther was a Swiss mountaineer who noticed that in Jurassic rocks of the Swiss Alps, the Jurassic rocks changed laterally, like you change from a channel deposit through to a Paleosol facies. So we have the channel sandstone here, Paleochannel facies, and we have a Paleosol facies out here. We can put in more Paleosols here, and we can also put in another channel. These are the Paleosols. Now, this is a lot more complicated than what Walther envisaged. Walther was envisaging a Jurassic situation where the sea was either coming in or going out, and so you had the deeper water facies that were on top of the shallow water facies, on top of the terrestrial facies as the sea was transgressing into the land, and then the opposite relationship as the sea was pulling out. Here it's a little bit more complicated, but it's the same principle. And the principle is that facies that are found in a vertical section, a single vertical section, probably represent environments that were side by side in nature. So this is the channel. Here's the channel. Here's the levee. Here's the levee soils. Here's the thick soil of the floodplain out here at the very, very top, one on top of another, in a kind of a seamless succession. We find these repetitive cycles, particularly in alluvial rocks, which give us a clue to the lateral distribution. In a coastal area, you go from the beach through the sand dunes, through the lagoon, and then the upland soils, a similar lateral relationship. Walther's facies law is the main way in which we can actually reconstruct the lateral variability of paleosols from individual measured sections. With the exception, of course, if you have this kind of level of detail and you have a volcanic ash or a paleomagnetic isochron to give you the actual landscape that existed at the time. So those are two ways, to reconstruct the ancient landscape from fossil soils. And it's quite intriguing and rewarding to try to do this from a sequence of paleosols. We get whole visions of ancient landscapes from sequences of paleosols in sedimentary successions. We can also, of course, follow soils uphill and down dale on bedrock surfaces at major unconformities. That's another place where soils are avidly studied. For example, the great unconformity in the bottom of the Grand Canyon is a whole complex of paleosols that were developed on different kinds of bedrock, ranging from granite through to older sedimentary rocks, basalt, and others. We can start to piece together these ancient soilscapes from the fossil record of soils. Well, that'll do it for topography. I'll see you next time.